Okay, welcome back to the very last part of our trilogy here. The Return of the Jedi of solving quadratics mentally, if you will. Just as exciting. We're going to put it all together. That's what I'm calling this. And the same examples in the beginning, right? Here's a quadratic equation. You're trying to solve it. We want to be able to tell the answers to that really easy. And here are the answers. And today, we're going to find out why. So, to review, we should be able to find the vertex of a quadratic by putting it in vertex form or completing the square. The same idea for us at this point. So x squared minus 10x plus 20. If you complete the square for that, you're going to get to this. And if you square that out, you're going to see it's the same thing. And that moved my vertex 5 to the right, 5 down. X squared minus 8x plus 15 is the same thing as this. I'm just double checking to make sure I didn't type something wrong. It's going to be plus 16 and minus 1 is 15. That's right. So we're moving 4 to the right and 1 down. All right. X squared plus 4x plus 12 tells me it's going to be plus 2 squared. That's what the 4 tells me. And that's going to give me a plus 4 at the end, but I need a plus 12. So that's a plus 8. And that's going to put the vertex at negative 2, positive 8. And this is going to give me minus 5 halves out here squared. If you square that out, you're going to get 25 fourths, which we'll write out so you can see. You get 25 fourths, but we have a 16 over there, which is, we have a 4. We have a 4 over there, which is 16 fourths. And this is going to be 25 fourths, so I'm going to have to subtract off 9 fourths to get back down to that 16. Okay, and that means the vertex is 5 halves to the right, so positive 5 halves is the x value, and 9 fourths down. Okie dokie. So I'm just walking you through a couple examples here where, so I'm giving you a quadratic and I'm showing you can do all the quadratic formula nonsense, not nonsense, the good stuff of it. It's a nice formula and it gets you all the way down to this answer here. Okay, so again, that tells you where a quadratic equation will equal 0 or a quadratic function will equal 0 when you do that. And that's really good for programming computers to solve stuff for us, and it's a great formula to know. But we're trying to do it a little bit less work. So let's come on down here and talk about why we like vertex form. So given the same exact quadratic equation, if we complete the square and drop it into vertex form, what you could do is do a little bit of algebra and solve that out. So I got the work right here. I'm going to do it again. What you're really doing is you're adding 5 to both sides. Then you're taking the square root of both sides, and something students forget a lot of times is to put the plus or minus out front. Okay, so that's a little hazard there. But you put a plus or minus because when you're taking the square root, if you square negative root 5, you still get positive 5. What are we saying? Negative root 5 times negative root 5 is still positive 5. All right, and then we would subtract 4 off of here, and we would get negative 4 plus or minus root 5. And you put the negative 4 out front of this instead of writing this plus or minus root 5 minus 4. It's the same as that thing. You can write it like that, but generally we want this number out front here. That's how you typically write it. Okay, so while that was not super duper easy, once we complete the square, we don't have to look up here at the quadratic formula. You got to write it all out. You got to plug it all in. You got to simplify it. You got to simplify the root a lot of times. Not that you won't have to in other ways, but quadratic formula, a lot of times you have to. And then you got to divide by this too. And students are just typical to messed up division there because they forget to divide one of the terms. Okay, when you do the complete the square thing here, it's really just you got to complete the square. That's the hard part. But then you got to add 5, take the square root, subtract 4. It's a little bit less intense. Okay, but I want to make it even less intense than that. So we're going to think about this graphically, which is why I wanted you to know where the vertex was. All right, so we're still going to have to take the quadratic we were given and think about where the vertex is. All right, so I'm hoping that we can just tell where the vertex is without writing out vertex form. You can write it out. Like again, you write as much as you want. There's no shame in that. I'm trying to get a little more fluidity with these things. That's the whole point. This is like an accelerated little special class. But when we get it in this form, it tells me that this thing is going 4 left and 5 down. And you can see that happening. Let's just switch to blue. We are going 4 left, 5 down. Okay? So that's where the vertex goes. And when that happens, what happens is this thing opens upward, and the zeros are going to be up here, splitting the difference between that -4. Like -4 is right down the center. That's called the axis of symmetry. It doesn't matter too much. It's what the parabola has symmetry over. You could fold it in half on that line. Essentially, it's the same thing, right? It will lay on top of itself. But the distance that goes out is the same for both of those, and that's what we need because I know we're at -4 already. Okay, and here's the big secret here. However far down we move the vertex vertically. So again, I move the vertex down 5 here. That's what happened. See this distance? It went down 5. I know that because the y value is -5. What happens is the roots, the zeros of this thing, move the square root of that number horizontally. So if I pull the vertex down 5, then I move the roots over square root of 5. But we go to the right root 5 and to the left root 5. So if I know the vertex's x value is here at -4, then I know the roots of it are -4, and we need to go up and down root 5. And that's how I know what the zeros of that thing are, simply by looking at x squared plus 8x, what was it, plus 11? Okay, that was the original thing, right? I feel very confident of that. Okay, good. Just want to make sure. Okay, so again, here's what I'm thinking. This 8 tells me that this is going to be an x plus 4 squared. Okay, what it really tells me is that the value here has to be -4 because it moved it 4 to the left. That's what this number does. And the 11 tells me, well, I want it to be a 16, right? Because the 8 tells me if this is a perfect square, this should be a plus 16, but it's not. It's 5 too small. And if it's too small, that means we need a -5 to get back down to it. Or you could think it's shifted down 5. It's too small. If it was 16, let's think like this. If it was x squared plus 8x plus 16, it would sit right here. That's what this is. X squared plus 8x plus 16. But we had x squared plus 8x plus 11. That's a difference of 5. It's 5 too small, which means it must be 5 below it. Like this, opening upward. And that's why we know it got pulled down 5 to get there. But I don't care that it got pulled down 5 necessarily to find the vertex. I care that if I pull it down 5 to get here, the roots go out root 5. And that tells me this number. And that's it. That's the whole process of finding these zeros. Relatively simple. And like we couldn't have started with that because you got to be able to get the vertex form first. And that's just a good skill to have. So the big secret, it's not really a secret. If you know where the vertex is, then you know where the x-intercepts are. Okay, and this is also very specifically for quadratic equations, right, that have just a 1x squared out front. All right, so like if we had a 2x squared plus 4x plus 5, we need to do a little bit different to get there. We can still do it. There's one extra step, and we got to deal with some fractions sometimes, so that's a little pain. So I'll show you a couple of those as we go along. But for the most part, I just want you to be able to solve quadratics when the coefficient out front is a 1x squared. Okay, so let's take a look at another one. When we have x squared plus 10x plus 18, this 10 tells me that it has to be plus 5 squared. It also tells me that if it's a plus 5 squared, I should have x squared plus 10x plus 25. But I don't. I have plus 18, which is 7 too little. Okay, so when I square this out, I'm going to get this. But I need to get back down to 18 because that's what was there. So that's why there's a -7 here, which is why there's a -7 here. Okay, and you can do a little bit of algebra if you want. Add 7, that's not too bad. Take the square root, that's plus or minus root 7, and then subtract 5, same thing. But graphically, without even completing the square, here's what we're thinking. This plus 10 tells me that my vertex should be at -5. And I put this on the paper so it's hopefully semi-easy to see there. But this value here is x equals -5. You can see the -5 value right there, okay? And the 5 tells me this number here should be a 25, but it's too small by 7, which means it's 7 below the perfect square. Remember, the perfect square would sit right here like this. It would come down, touch the x-axis, and go back up again right at the -5. So if it's 7 too small, that means it's shifted down 7, which means the zeros are over root 7, up root 7 and down root 7, left root 7 and right root 7. So the answers are -5, which came from this 10, plus or minus root 7, which came from how far off this number, 18, was from the 25. All right, one more time, a little bit less work. We have the x squared plus the 4x plus 2. Okay, the 4 tells me it should be x plus 2 squared. Okay, so the vertex has an x value of negative 2. That's what this does. Remember, if you have any parabola, x plus 2 squared, plus any number back here, or minus any number back here, the vertex x value is still negative 2. This tells you what the y value is, okay? So that's why I know the x value is negative 2, and that's why I know this number here is negative 2, because I'm going to pull the vertex down or up from negative 2, and it's going to be centered there. And then we're going to go up some and down some to find the x-intercepts. Let's make sure you get that. No matter where the vertex is, boom, 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 here's the vertex at this x value, the distance to this 0, and the distance, that's a pretty ugly looking bracket, but it'll be okay. That's not much better. But whatever this distance pulled down is, I don't use k, whatever it is, this value is going to be the square root of it. All right? So, and it's going to be plus that and minus that. That's why we see that. So we have the negative 2. I knew that had to be here. If I squared x plus 2 squared, I should get a plus 4. It should be plus 4, but it's not. Okay? It's a plus 2. That's what I'm saying. Hey, the constant's a plus 2, and it's 2 units too small, which means I'd have to pull the vertex down. Let's just graph it. I know it's at negative 2, but it's 2 units too small, so it's 2 below where the perfect square would be. So it opens like this. So it looks like this. Okay, and that this doesn't go through there. It goes through like right a little bit before 0. Okay, and it's negative 2 plus or minus root 2. Let's do it one more time. Here we go. This value tells me 9, because if I square it out, again, I don't want to write this over and over again if I was solving this in my head, but I'm writing it out for you to see this. It should be x minus 9 squared. That tells me that my solution to this is x equals 9 plus or minus something, okay, because I'm shifting it 9 right. And then how far down I pull it or how far up I take it is going to change what's in this plus or minus. There's a 40 here, but if I square out this 9, I'm going to get 81. 40 is 41 below that. So I'm taking this quadratic, which should have a vertex at 9, 0, and I'm moving it down 9. So now it's going to open like this. Okay, and since I moved it down, not 9, I'm sorry, I moved it down 41. And because I did that, these roots are going to be over root 41 from 9. So we're going up and down. That's what's happening. So it's 9 plus or minus square root 41. Okay. And down here to show you this, a super sweet thing about this is we're not going to be able to factor ones that have imaginary roots. Like you have to use the quadratic formula or complete the square. But if you can do this, this still works. Okay? It just gives you imaginary roots. You just got to think about where the vertex is going to go. So let's take a look at this one. The minus 18x there, right here, tells me this should become minus 9 and squared. Okay? That means this number here should be an 81, but it's not. It's too big by 9. So again, x minus 9 squared would sit over here like this at 9, just like that. That's what this looks like. But that is also this. If you multiply it out, right? Boom, 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 we get that. That's what this is, okay? But that's not what I have here. I have plus 90, which means I need to add 9 to this to make that happen. The 81 has to add 9 to get to 90. Okay? What that means is it moved this up 9. So it happens to be centered at 9 on the x-axis, and I also have to pull it up 9, which is fine. It opens up like this. This distance 9. Now, this never hits the x-axis, right? So it doesn't have x-intercepts, but it still has roots. The difference between like x-intercepts and roots, roots encompasses x-intercepts. Roots means like what do you plug into this to make this thing equal 0? X-intercepts means where does it hit the x-axis? A lot of times they're the same thing if they're real numbers. Not a lot of times, they're always the same thing if they're real numbers, but if they're imaginary, then they're not x-intercepts. They're just called roots. So anyway, because this thing never hits the x-axis, the roots are imaginary, but since I moved it up 9, it's kind of weird. It's hard to graph this. The roots are still up the square root of 9. They're just imaginary, so it's I root 9. All right, and that's what we get. We get 9 plus or minus I root 9. And because root 9, we can actually take the square root of 9, we should simplify that. So it's actually 3, so 3 times I. And without having to do the quadratic formula, which I could do for you right here if you wanted to, it looks ridiculous. You got to do x equals, the opposite of negative 18 is positive 18, plus or minus a square root of 18 squared, that's 324. Great, minus 4 times a times c. Oh my goodness, all over 2 times a. And you got to simplify all this junk out. This is 360, subtract, subtract, subtract. It's going to be a pain in the butt. All right, but anyway, you could do it. You could do all this workout if you want, or you could follow what I'm saying here and be like, oh, it's centered at 9 because of the 18. That's easy. This should be an 81. It's 9 too big. It got pulled up 9. Great. That means the roots went out root 9, which is 3. But they're imaginary because it got pulled up and it never hits the x-axis, and that's what happens. Okay. So we're going to do a bunch of examples here. I'm going to go to Desmos, though, real quick and just show you what's happening graphically so you can see this. I had to look up the name of the third Star Wars movie because I knew it was Return of the Jedi. I just had to make sure before I recorded the video. Anyway, let's go ahead and graph. I'm just going to graph x minus 4 squared, okay? Okay. And you can see that the vertex is right here at 4, 0 until I add a number to it. So when k is 1, you can see it has moved up 1 right there. 4, 1. I'm going to make k 0 again. So all I'm doing is changing it to a 0. Boom. Okay, so what happens is, again, as we're going to look where we have real solutions so we can actually see them on the graph. When k is big, like positive, I mean, it takes it up, and those roots are imaginary because it never hits the x-axis. But if you pull it down, you can see both the roots, okay? But look, check it out. When I pull it down 1, when I make k minus 1, it pulls it down 1. So this is at 4, negative 1 now. And you can see the roots are at 4, up 1, which is 5, and down 1, which is 3. All right? When I pull it down 2, it's kind of hard to see it happen because now I'm down a distance of 2, and the roots should be 4, up, not up 2, up the square root of 2, which is 1.414 and some change, and that's why you see 5.414, and down the square root of 4, which is that. Okay, so it's harder to see when the root we're taking isn't like a nice even number. But so we'll go down to the next number that is a nice even number, 4, right? If I pull it down by 4, well, look at this. Oh my goodness, we're down 4. The roots should be up 2. Remember, we're centered at 4 right now, so up 2 is 6, and down 2, which is 2. All right? So you can solve it by the, again, quadratic formula. You can solve it by factoring if you get these whole numbers here, which works out nicely, or you can solve it the way I'm doing it, which, again, is just in your head a little bit less manipulating math. And the next one we can do and show that this is happening again, it's just the same exact thing, is if I pull it down 9, so we're all the way down here at 4, negative 9, then the roots should be up 3 from 4, which is 7, and down 3 from 4, which is 1. It just works over and over and over again. All right. So, again, disclaimer here, and I'll do it at the end of the video. How do we handle when we have a coefficient that isn't a 1? All right. But disclaimer, this only works when the coefficient is 1, which might make it seem like this is kind of a weak technique. But again, this isn't to solve all quadratics. It's to make you a little bit more fluent, and so you're not too scared of quadratics, and you know what the graphs look like when the coefficient is 1, which happens a lot of times. All right. So let's come on down here. I got this big whole table here. And the whole idea behind this is the plus 8x tells you that this should be, when you do this, x plus 4 squared, which lets you know you're going 4 left, which means the value of the vertex is negative 4. Okay? If you squared it out, perfect square should be a 16 when you do that, but it's not. It's a 13, which it's 3 less. 13 is 3 less than 16, so it must be 3 down. So the roots must be negative 4 plus or minus the square root of how far down I moved it, which is root 3. For the next one, the plus 6 lets you know it's going to become the plus 3 squared, which is 3 left. That's x minus, or x is negative 3, right? That turns into this over here. A perfect square says this should be 9 when we square it out, but it's not. It's a 7. It's 2 less than what it's supposed to be if it was a perfect square, so it must be 2 below it. So it's negative 3 plus or minus root 2. Next one. So look, we're going to do all these like relatively quickly, and we're showing like if I gave this to like a student who didn't know what I was doing, they'd see this and be like, oh my god, this is a ridiculous amount of work for me to do this. And maybe you think that right now. That's fine. But if this is clicking and you're seeing the pattern that I'm saying, this is not going to take us that long to solve these. And nowhere are you ever going to have to machine gun through like these quadratics, okay? I only set out to do this because I see a lot of students struggle with this after they learn it and they forget all about quadratics. Okay, so the plus 10 tells me it should be x plus 5 squared, which means we're going 5 left. That's x equals negative 5 is my vertex. That tells me this part. If negative 5 is the value of my vertex, x plus 5 squared, right? That's going to give me plus 25 when I square it. But I have a 29, which is 4 too big, which means it must be up 4. And that tells me I have imaginary roots. Let's go back to how this graph looks. I know it's at negative 5, but it got moved up 4. So this is what this graph looks like. And it's nice to know what a graph looks like. You see exactly what the picture looks like. And in calculus, a lot of times you care where things are positive and negative. So if you know what the graph looks like, you know it's always positive. Well, in this case, but if you also know what the graph looks like, you know where it's positive and negative, and it's a whole lot easier to think about rather than having to handle all the algebra. Okay. Anyway, it got moved up 4. So they must be centered at negative 5 plus or minus the root of 4, but it's times I because they're imaginary because there are no x-intercepts here, okay? The roots are imaginary. And because the square root of 4 is 2, we just get 2i. All right. Let's keep going. This is 1 because of the negative 2, right? It should be x minus 1 squared. If you square that 1, you should get a 1, but we don't have a 1. We have a negative 3, which is 4 below. It's 4 less than what I need. Negative 3 is 4 less than 2. Where did that come from? Negative 3 is 4 less than 1. No. Negative 3 is 4 less than... What was I typing here? When you square the 1, you get a 1. There we go. So now I've said... I'm trying to show you how to do this, and Oh, yeah. Okay, should be a plus 1, but it's a minus 3. This is right. It's still 4 down. Negative 3 is 4 less than 1. That's all. This should just be a 1. Come on, Mr. Smith. So it got moved 4 down. Okay, I got all these numbers floating around in my head. So what that means is this should be 1 plus or minus the square root of 4, which is 1 plus or minus 2. And we can solve 1 plus 2 is 3. So there's a 3. And 1 minus 2 is negative 1. Those are the zeros of this thing. And that checks out because if you were to graph it, the value of the vertex is 1, the x value is, and it's minus 3. So we're down 4 from that because, again, this should be a 1. So we're down 4 from that. So this distance is 4. Okay, but because it has a nice square root, you're going to see that the roots are nice numbers. Because if we go down 4, that means this must be up the square root of 4 and down the square root of 4. So it's 4 plus 2. 4. Why am I doing 4? 1 plus 2. Because we're centered at 1, gang. There we go. 1 plus 2 and 1 minus 2, which is 3 and negative 1. Whew, I got flustered there because I put this stinky 2 here instead of a 1. Okay, let's keep going. X squared minus 4x minus 1 says that this should be a plus 4. That's what I know. I also know that this is going to be a 2 over here now. Okay, it should be a plus 4, but it's a minus 1, which is 5 below where it's supposed to be. So you move it down 5, you're going to get up and down root 5 of the roots. Okay, let's get busy. Here we go. I'm going to fill these things out for a couple of these, but then I'm just going to jump right to the answers here, okay? Just so to explain our reasoning here. That minus 12 tells me that it should be x minus 6 squared, which means the x value is at 6. So this is 6 plus or minus. If this was a 6, this should be plus 36 when I complete the square, but it's not. It's a plus 30, which is 6 too small. So we drag it down 6, which means the roots go over root 6 or up to the right root 6 and to the left root 6. Alrighty. We have a 20 here, which tells me that the x value's vertex is going to be negative 10. And if I square that out, I should get plus 100. But this is 20 too big. So we're centered at negative 10. But it's 20 too big. So graphically, here's negative 10. The vertex is up 20. Boom. That means they're imaginary, but it moved up 20. So it's going to be imaginary roots that have a root 20 attached to them. All right, and root 20 simplifies, so it's really, let me zoom in here so I can write this in here. It's really negative 10 plus or minus 2i root 5. Let's make that 5 a little nicer. Okay, probably looks the same. All right. Let's keep going here. X squared minus 8x tells me that this should be x equals 4 is the center of that. If you square that out, you should get 16. But I have 20, which is 4 up. Let's write that here. That's 4 up from 16. So it got shifted up 4, which means we're going to have, that says imaginary. Let me write that again. We're going to have imaginary roots. I don't know why I stopped there. Imaginary roots. Okay. So they're centered at 4 plus or minus the square root of 4. That's how far I moved it up, but it's imaginary. So it's I root 4, which is really just a 2. So we can put the 4 there, but root 4 is just 2. So you might as well just say 2i. There we go. All right, so we're going to rock these out real quick here. The 14 lets me know this is -7 plus or minus. The 30 should be a 49. It's 19 too small, so it's down 19, which means we have real roots that are root 19 away from -7. All right. -16 here tells me that we should be centered at +8 plus or minus. This number should be a 64, but it's 164, which means it's 100 too big, which means it got shifted up 100, which means they're imaginary, and they're times the square root of 100, which is 10. So 10i. The -6 there tells me this should be 3 plus or minus. This should be a 9. Let's write the 9 there for right now so we can see. We got a -5. We got to work this out. But we should be a 9, but it's 14 too small. So it's plus or minus root 14. Now we get the fractions happening now. So this is a 1. We'll write this out first couple of these. This should be a 1. All right. This is a 1. I'm sorry. But that means that when you factor it, it should turn into an x plus, not when you factor it, good God, when you complete the square. It should be x plus a half squared. All right. Which means our x value of our vertex is -1/2, which means this is -1/2 plus or minus. And then all we got to do is find out how far off we are. Okay, it's not -1/2. It's too big. It's +2. Okay, so what's this column for? Perfect square. Okay, so if it was a perfect square of -1/2, the number there should be a 1/4. But it's not a 1/4. It's 2, which is 8/4. And the difference between them is 7/4, which means that the constant I have is 7/4 too big to be a perfect square, which means it got moved up 7/4. So this is plus or minus the square root of 7/4. And the square root, just while we're here, the square root of a fraction is just the square root of the numerator and the square root of the denominator. So root 7 of root 4. And that's really just 2. So you can do, and you got sometimes like students get, I definitely did this in high school. When you get sloppy with your root, you might be like, oh, root 7/4. And you're like, is that the square root of 7/4 like that? Or is it the square root of 7/4? It's hard to tell when you get halfway in there. So just be careful how you write it. This is the square root of the whole fraction, root 7/4. But if we reduce it, it's the square root of 7/2. All right. -3 here tells me this should factor again in 2x minus 3/2 squared is what's going to happen. So the x value of my vertex is 3/2, which is just 3/2 plus or minus. And if you square this out, you should get 9/4 is what we should get. But we don't have 9/4, we have 1. Okay? And that this is, 9/4, we have 1, which is 4/4. So it's 5/4 below this. So the constant we have is 5/4 too small. Which means, just to graph it again, if you're still with me, we're centered at 3/2, and it's pulled down, it's shifted down 5/4, which means my roots have to be the square root of 5/4 up and down from 3/2. And since we're going to do the square root of the fraction again, that's going to be square root of 5/2. All right. So let's just jump right over here. We got a 5, which means the vertex is going to be at -5/2 plus or minus something. -5/2 means my constant should be 25 fourths, right? We should have 25 fourths here. But we have 9, which is 36 fourths is what that number is. And it should be 25 fourths for the perfect square. So it's 11 fourths too big, which means it got shifted up. Okay, it's bigger than the perfect square, which means we moved it up. We moved it up 11 fourths, which means this is going to be plus root 11 over 2. And last but not least, if x squared plus 9x plus 30, we know that we're going to have plus 9 halves if we were to complete the square here, which means the x value is at negative 9 halves. So it's negative 9 halves plus or minus. And when you square that, you should get 81 fourths. All right, but we don't have 81 fourths. We have 30, which is 120 over 4. Okay, and that's bigger than 81 fourths, which means this thing got shifted up. And it got shifted up to get to 120 from 81. You got to add 19 and then 20. So we got to add 39. So it's 39 fourths too big, which means we moved it up 39 fourths, which means our roots are imaginary. Oh man, that means my last ones were imaginary also. Almost missed that one. Okay, so this is I root 39 over 2. Okie dokie. Did I do that on another one too? I think I did. Should have been one. Yeah, this one right here should have imaginary roots. So normally I wouldn't miss that. I'm trying to rush and get these done here. Okay. So when that's a pitfall of this method, I guess. Like you could forget to make it imaginary, which is why it's good to kind of think about if it's too big or too small. If we go back to that example here real quick, but hopefully you noticed it when we went through it. I said the number we need is 1/4 to be a perfect square because it was a 1 here. But I have 2, which is 8 fourths. So it's 7 fourths too big, which means it got moved up 7 fourths, which means my roots are imaginary. Okay. And last but not least, if you're still with me here, let's say we had, just to go through a couple examples, let's say we had something like, let's make this easy for us for a second, plus 9 equals 0. So we want to solve one where the coefficient isn't a 1. It can be negative. It doesn't matter. Let's make it negative. It doesn't even matter. All right. Well, it turns out that if you take what I just do, if you take a quadratic equation. So let's go with, let's graph the one we have. Negative 2x squared. What I do? Plus 8x. Let's make sure I'm working with the same one. Plus 9. Negative minus 8x plus 9. Okay. Let's go back and change that. Minus 8x plus 9. What have you done? Minus 8x plus 9. All right, it looks like that, all right? But if you take this and divide everything by negative 2, okay, which is the coefficient out front here, right? So we just divide everything by negative 2. We get x squared plus 4x minus 9 halves, okay? And what that does is it changes the graph. Absolutely, it does. The vertex is no longer in the same place. However, if you look at this, the zeros are in exactly the same places. Okay, because if this equals 0, then dividing it by 2, it's still going to equal 0. So these both equal 0 at the same exact places. All right, so my advice to you is if you want to use this method and you have a coefficient out front that's not a 1, just divide everything by the coefficient, and you can do it on this. Now, there's going to be fractions, so you might have to write some stuff down. But I still think this is a little bit nicer than going all through the quadratic formula and just all the ways that you can mess this up. Okay, not you specifically, but anybody, even me. I'm making mistakes all over the place here. So if you divide this by negative 2, this turns into x squared plus 4x minus 9 halves. And I solve that equation instead. So the plus 4x tells me negative 2 plus or minus. That's what that does. All right, but that's because I know it's going to be, again, x plus 2 squared. Because when I square that out, I get x squared plus the 4x, but I also get a plus 4. But I don't want plus 4, I want minus 9 halves. So I need something here that's going to take that plus 4, that's right here, and drag it down to 9 halves. But 4 is really 8 halves. So if I need to take that down to negative 9 halves, then I need to subtract off 17 halves. And that's what will be here, which means this is going to be the square root of 17 halves. And that's how you can handle it if the leading coefficient is not 01. Again, it changes the vertex, so you can't find the vertex like that way. And you can do some other stuff to find the vertex. That's not my concern right now for you in doing this. But you can still find the zeros like this. All right, and just to show you this, like -2 plus root 17 halves. If you type that in, -2 plus the square root 17 over 2, look what you get, 0.9154, and look what you get right here, 0.915, and kind of the end there, but it's really 0.9154759474423 is really what that number is for both of these. All right, so go forth and be awesome at solving quadratic equations. Stop in and see me if you're long reach and let me know, and we can practice quadratics together. How fun will that be? And if you're in my math class, hopefully this makes calculus or geometry or pre-calc or whatever class it happens to be a little bit easier.